and thank you for being here today. So I'm going to talk about a decision support tool that I'm actively developing for optimizing assisted gene flow for Western North American forests. So this is a screenshot of the tool. It's called the Climate Adapted Seed Tool, or CAST for short, and it's publicly available at this URL if you want to check it out and play with it yourself. It currently only provides coverage within the state of California, but the idea is to expand it to other states. That process is relatively simple as opposed to all of the other parts of the tool. So one of the main intentions of the tool is to build on what's already available in the current suite of seed source decision tools by providing these quantitative empirical estimates of how well different seed sources will perform at user-specified planting locations, and to provide them in units that managers are already familiar with and related to their management objectives. So two of the metrics the tool currently provides are amount of CO2 sequestered per acre and the amount of timber produced in units of board feet per acre for different seed sources. And I'll actually go ahead and switch over to a live version of the tool so I can demo that. So selecting a planting location, you can just click on the map or type in a latitude and longitude. You can also specify the planting location by seed zone or map the seed source by seed zone, but here we'll use the precise planting location and map by raster. So in green, we've got the best matches for the seed zone in terms of how well adapted seeds from that location are projected to be for the planting location in the year 2040. The tool currently defaults to the year 2040, but you can adjust this. You can also adjust the metric here, lumber produced, and there's a number of other metrics that you can look at there as well. And then you also get this table of candidate seed sources, and this is displaying by seed zone elevation band on the right. So we can look at decline in productivity. So that's how well the seed source will perform relative to a seed source that's well adapted to the climate that it's growing in. So a 5% decline in productivity represents 5% less live tree volume, taking into account both the effects of mortality and growth rate. And then we've got confidence limits on decline in productivity, and then, of course, our additional metric right here. So there's a bunch of other things we could look at, including this examine match feature, which I encourage you to check out, and a bunch of the other settings that you can look at. But for the sake of time, let's transition to looking at the underlying models that go into the climate adapted seed tool. So I'm currently working with data for over a dozen different species, and a big thank you to Greg O'Neill for helping compile these different data sets. I've done some preliminary analyses on almost all of these different data sets, but there are nuances between the different data sets. And in terms of data sets that I've gone through with a fine-tooth comb, and I'm satisfied that I'm interpreting all of the metadata correctly and cleaned any erroneous measurements contained in the data sets. There's 4 species that I'm looking at more closely. And so these are the planting locations and then the seed source locations for those 4 species. So this is site by provenance means for relative volume per hectare for data from lodgepole pine, from the Illingworth study and a few additional sites. And the question I'm asking here is, what is the shape of the response function that makes the most sense, that fits the data best for climate transfer functions? The common shape used is a quadratic function, but does that perform well? You guys are probably familiar with a plot that looks very much like this. Seeds from locations most similar to the planting location tend to grow best at the planting location. And you don't need to look at data to see that. You could just look at demonstration plantation, where essentially this is the right side of this curve. The trees here are from the coldest climates, and trees here are from relatively warmer climates. So we can add one metric on top of this, or a summary on top of this. This is just the moving average response of the data, average to values within half a degree Celsius. And we'll use this black line, sort of the overall moving average shape of the data, to compare that against different shape transfer functions. So the first one we can look at is the quadratic. This is the most often used shape used to fit provenance test data. And one problem that jumps out, of course, is that it can predict negative values, which are impossible for the response metrics that folks are interested in when they're fitting climate transfer functions. We can improve on that by using a non-negative quadratic function. And you can see just through visual examination of how close this curve is to our moving average, and through our leave one out information criterion, the non-negative quadratic performs much better than the quadratic function. The two other shapes that we're looking at are the asymmetric Cauchy and the asymmetric Gaussian. And you can see both, if you zero in on this portion of the curve or this portion of the curve, the asymmetric Gaussian does a better job fitting the data. And look at that beautiful response function right there. So this seems to be generally the case for data for other species, data fit to other climate variables like mean annual precipitation or mean cold month temperature, and at different ages as well. The asymmetry turns out to be more important, at least for this data set, at different measurement ages. So on the left, we've got relative volume per surviving tree. On the right, we've got relative survival. And you can see, especially for the younger ages, there's a fair amount of asymmetry in these relationships. The other thing that you can see that jumps out is that climate transfer functions tend to get steeper over time. But by the time you get to about 10 years, at least in this case, the transfer function seems to stabilize. There's big differences between those younger ages, but relatively less differences in the shape of and the steepness of the climate transfer functions past age 10. So this is a look at the transfer functions currently used in the climate adapted seed tool. So it's limited to three-dimensional functions because of the correlation between these different climate variables. You don't want to include two highly correlated variables in the same model. And then we use multi-model averaging to create an ensemble model of those different models. This plot on the right, we can also look at in 3 dimensions right here. So you can see that the sensitivity to mean annual temperature difference is larger than the sensitivity to mean annual precipitation difference. See that here, and also see a little bit of asymmetry in that response function, and in this response function here. It's mean cold month temperature and mean annual precipitation. So all of these metrics are leave one out cross-validated performance metrics. You can think of the information criterion metric as similar to Ikaki's information criterion, except in this case, it's actually does a better job of predicting out-of-model performance because it uses that leave one out criteria, where the model is fit iteratively, each time leaving one data point out, and then that one data point is used as an out-of-sample point to evaluate how well the model performs on data that wasn't used to parameterize the model. This R squared, leave one out R squared, is a little bit lower than it would be for data internal to the model that was used to parameterize the model, because it's calculating the R squared for out-of-sample data that wasn't used to fit the model. And then the Bayesian stacking weights also use a leave one out procedure to determine the weights of the relative models in the ensemble model. And it's a little bit different than the way that frequentist statistic model weights typically work, or AIC, Ikaki information criteria information weights work, in that the weights aren't just determined by the information criterion score. The weights are determined using that leave one out procedure to iteratively adjust the weights of the different models until you get the best out-of-sample performance. This tends to result in models that provide different information from the other models that are included performing well. So mean annual temperature and mean cold month temperature are very tightly correlated, whereas temperature differential isn't as tightly correlated with those those temperature variables. So that's why you can have a model that doesn't have the highest individual information criteria performance, having fairly high model weight in the overall model average. So that's the model, the ensemble models currently used in CAST. Let's look at where the models are going. So on the bottom here, this is a similar model comparison table. You can see those three-dimensional transfer functions here. You can see you get much higher predictive, out-of-sample predictive performance if you transition to including multiple climate variables in the same model all at once and fitting those variables simultaneously. So to do that, because these climate variables are correlated, you have to use principal components. And you get pretty good performance just using the four principal components of these four climate variables. In terms of model averaging, you can get some different information by adding additional climate variables in there. But these four climate variables seem to be some of the best and most important variables. So that's the direction that the models, the climate transfer functions in CAST are going. I'm still working on model evaluation, wanting to make sure I get this right before we update CAST with the newest and more accurate models on the back end for those climate transfer functions. So what do we see in terms of differences between species and their climate transfer functions? So on the left, we've got an example comparing lodgepole pine and ponderosa pine. Vertical axis is decline in volume, and then we're looking at mean annual temperature difference. And you can see the transfer functions for lodgepole pine and ponderosa pine are very similar in terms of what they're predicting. The one main difference is that ponderosa pine has much larger confidence intervals due to the more robust data for lodgepole pine and sparser data for ponderosa pine. If say you didn't have data for ponderosa pine, what this suggests is that using data for lodgepole pine would be a very good first approximation for ponderosa pine. Of course, this is just looking at a univariate response function, so take that for what it is, but my other exploratory analyses comparing transfer functions between species also suggest that using a transfer function for a different species is going to give you a better result than, say, just using the local seed source. And then we can compare loss of volume at 3 degrees mean annual temperature change across several different species, and we see generally that confidence intervals overlap. In some cases, that's not the case, like the difference between Monticola and Contorta. But generally, take-home message here, while there do seem to be differences between species, and we can better optimize climatic transfer by fitting climate transfer functions to individual species. If we lack data for a species altogether, we're going to do better by using a transfer function for a different species as opposed to not using a transfer function at all. So this is just a look at the growth and yield functions that are used in CAST to provide those carbon dioxide sequestered and lumber produced metrics. And so these are fit FIA data from the 5 most western states in the United States and fit monad type functions. So you can see larger stand age is associated with more stand volume. Higher temperatures are associated with more stand volume. Incidentally, this is data fit to Douglas fir. And then moderate levels of precipitation are associated with the highest levels of productivity for Douglas fir. And with that, I'll say thank you. I couldn't have done this without support from all of these amazing people.